Good afternoon. Today is the first in a series of Intrepid webinars, recorded webinars. My name is Des FitzGerald. There are going to be two parts in this webinar today. The first one is to do with the history of good gridding practice in potential field data, some theory and methodology for gravity and magnetics, the standard scalar entities which are much in practice, and then I'm going to show you some extensions to gradient gridding and tensor gridding. So the purpose of the talk today is to go over taking an irregularly sampled field, for instance a gravity field, and create a regular grid or mesh, gathering the observations and or the gradients and using the principles of physics to produce a best or an optimum representation of the field on a gridded basis. What does gridding involve? Well, in its simplest form, you have a geophysical database, which is simply a location of field observations, which therefore is easting, northing, and elevation, and the observation of a gravity observation or a magnetic field observation. Our gridding tool is integrated. It has a graphical user interface, and behind the scenes it has an implementation of every function described using the Google Protobuf messaging language, and this of course we publish. So every feature and option available in the tool can be driven either by the graphical user interface, or if you're into scripting languages and optimizing processing, you can also drive the equivalent, get access to the equivalent algorithms through the batch interface. And of course the output is a representation of the field as on a regular mesh basis. So, as a grid is an interpolation between measurements. So in this screenshot here you can see the black dots, and this is a mock-up of some of the processes. In fact, it's part of the data set we're going to grid later in the live demo around the Amadeus Basin. So you see a regular sampling on the left-hand side of the screen. You see the 11-kilometre style gravity stations. You move into a period of a portion of higher density, perhaps half a kilometre, and then you have 4 kilometre type spacing over here on the right hand side, and then you have observations of gravity along the tracks and roads. And there's an impact structure, and there's been some oil exploration in parts of this area, so you even have areas of even higher density gravity. So this is what we call by variable sampling density field. And how do you grid that data to honour the observations and the frequency content and wavelengths that have been actually measured. So the highlights of the tool. So the idea is that the intent is to use appropriate physics principles, and in this case that implies honouring the curvatures. We know that the second derivative of potential field is continuous, and that is in fact a statement of a smooth curvature. We always use 64-bit precision at the very least to do the internal arithmetic, to minimise any sort of errors that might be introduced due to rounding. The gridding tool has been designed to not just grid one data set to produce one grid, but it has been designed to take up to as many data sets as you choose, stored in different databases, and the merge of the data is done dynamically to produce one grid output. So, as I state here, there's been up to 7,000 data sets produced. The types of observations that can be put into the tool, which the standard scale of TMI and gravity, as I've mentioned, and we can make use of enhanced representation of the scalar field by also honouring gradients, both horizontal gradients, full vector gradients in the 3 dimensions, and tensor gradients if you're lucky enough to have those as well. Before you create the grid, it's sometimes desirable to transform the dataset fields for various reasons. One of the things you might wish to do is do a projection conversion on the fly. You may only want a subsection part of your database to zero in on an area of interest. You may wish to apply a line filter of some description, a Naudi line filter that's available. And one of the particular features that Intrepid has is a way of managing the observations when there are multiple observations that occur in one cell in the grid that you're about to produce. So we allow you to set first in, last in, nearest to centroid, or averaging, and this is a user settable parameter, and at times that becomes very, very useful. When we come to start to interpolate the data, we allow the option of 2D splines, 2D once in the east direction, say, or once in the north direction, or if you're producing a rotated grid, along the rows and then across the columns. That's the first primary tool that honours curvature while interpolating the data. Another way of producing the initial grid is what we call the nearest neighbour, or the natural neighbour method, which is based on a triangulation, coming up with a local neighbourhood of triangles, and from that we interpolate between the triangles. The next gridding method is this multi-grid, which has been designed to suit this case I've mentioned already of variable data density. So we start with quite a coarse grid, get an idea of the 2D curvatures at the longer wavelengths, and then we progressively sample that down to a finer cell size, preserving the longer wavelengths that are not supported by observations at the finer cell size. And the final processing method for interpolation is to do with curvature gradients themselves, tensor gradients. We've patented a method where we interpolate the full tensor gradients in one operation. This has been termed the spherical linear interpolator, or SLIRP method. You can look it up on Wikipedia. We've adapted it not just to the one-dimensional case, but we've got it in 3 dimensions and for the full tensor. So here's a slide which demonstrates the slight differences between the spline curve, which is the dashed, honouring the observations, but you can see there's a slight variation between the predicted intermediate values compared to minimum curvature. So they don't produce exactly the same grid. There is slight differences, and both of these technologies would be claimed to support the physics. Minimum curvature works in 2 dimensions. Akima is working in 1 dimension, but in this case we're only talking about a mocked up profile of data, in which case it's an illustration of the difference between the 2 technologies. Very similar but not the same. I think the point to note is that splines can undershoot and overshoot. If you look at the bottom right hand corner, just this point here, you can see that the estimate from the spline will be less than the observed minimum data set, and that's a characteristic splining. Splinings can undershoot and overshoot. Minimum curvature tends not to do that. Having created an initial grid, we have another stage called the grid refinement stage. And the grid refinement stage adapts depending on what you choose and what the data types are that you are choosing to grid. It can be as simple as a Laplace smoothing operation or a box filter, which is a fairly coarse method. The traditional Briggs method, invented at AGSO, the minimum curvature method. Intrepid has a direct link back to that invention, being sponsored by Geoscience Australia or AGSO, and the gridding algorithm that you see has a direct link back to that original invention. The recent invention of the MITRE method, which is minimizing tensor residuals, we recognize that the minimum curvature method the physics of that is based on the Laplace condition from tensor arithmetic. So it's the minimum curvature condition is a second order type curvature, and since we're measuring second order curvatures with tensors, we have to go to a third order minimizer, and we've done that, and so you come up with a 7 by 7 by 6 kernel that we apply through the tensor grid to minimize the residuals and to honor the physics. Here's a facsimile of what we mean by minimum curvature in the traditional finite difference representation of a grid. So if the observation in point that we're wishing to estimate is the black square, the neighbouring cells maybe have observations or estimates already calculated, and we wish to improve the estimate of the one in the middle by looking at what the values around it in its immediate neighbourhood. And you can see what we call the 13 active cells. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there are 13 cells in play with this what we call a 2D spatial convolution kernel. And we progressively move our operator, our 13 kernel operator, across the grid, across the columns to the right, then move down the row, and then go across, and then across. Then we come back through the grid in a reverse motion, and then go forward, and we iterate through the grid, seeking to minimize the curvature residuals. Now that 13 point operator, if you imagine that those infilled dots represent those 13 points, you imagine the white open dots to mean cells that are not nearby cells that aren't being looked at. And if you imagine your flight lines or observation points to be along those lines that are dashed, you can see that your operator, if there is 1, 2, 3, 4, 5, no more than 5 cells between one line and the other, the operator can span between the observations. And that's about as far as you can go with a traditional minimum curvature operator without getting so that the grid remains supported by real observations. This is in fact an indirect way of pointing out that there's a restriction in potential field geophysics gridding, that you can't expect to be able to create a finer representation of your data if you're going to use an operator like minimum curvature, where the number of cells between the lines exceeds 4 to 5, because you get classically sagging if that's what you try to do. You get sagging. So Intrepid has improved that minimum curvature by extending it to a 25 point kernel, and here's that stencil here, and this is already quite an important extra radius of influence. It allows you to get, for the same survey data, to decrease the cell size and therefore have a higher resolution representation of the field. And the only penalty is that you have to use an improved minimum curvature kernel. So I've started to allude to the concept of honouring the location of the observations. Intrepid recognises when you want to maximise the value of your survey data, and as it's represented in a grid, honouring where the data really occurs is pretty important. So Intrepid has put a lot of effort into this, and we've come up with some special improvements. So the first thing there's a subcell scheme, and what we've done here is say that if the observation, say, occurs not at the centroid, which is the black square, but at the asterisk, which is where the observation really is, you have a gradient of the field in the y direction between B3 and B4, and a gradient of the field in the x direction between B1 and B2. So you have some idea of the local gradients from the observation point to the centroid, where you have to actually estimate the field while honouring the observation. So you not only know what the observation is in a subcell scheme where it is, but you want to be able to use that where it really is to influence the local estimate of the field at the centroid. So that's what we call a first level honouring the observations strategy. What we've done in extending the technology is not only have the observation influence the immediate nearest centroid, but the three others in the vicinity, and that's an extension that Intrepid have implemented in their gridding technology. So this is a unique grid refinement option to our minimum curvature algorithm. In honouring the key original observation, the observation is located to the nearest 1/64th of a cell dimension, and the three nearest neighbours also see the observation. And we've increased the order of the finite difference smoothing kernel from 13 up to 25 terms, and we're using a third order error. We therefore get a resulting third order error term rather than the second order error term as a benefit. Finally, coming to the specification of the output grid, we can have a standard or scalar treatment for this the grid, and as I said, the industry standard tends to be 1/4 of the line spacing, so by default the tool will estimate that for you and produce a default cell size that honours that. If you're dealing with gradient data, the anomalies can be formed and represented where they really are, and they don't just end up centred on the flight lines. One of the tests of your gridding algorithm, which I'll show later on, is that for scalar gridding, the anomalies are forced to lie upon the lines of observations and cannot occur outside that. If you have that occurring, you have a poor algorithm. But if you're lucky enough to have gradient data, well, the anomalies can be shifted to where they really are in the context of between the lines or between the observation lines, and that's a pretty important improvement. So here's a representation of some vector gradients with the flight lines. You can see it's tilted, and you have some tie lines coming down from the top to the bottom, and more or less horizontally you have the flight lines and the gradients, say of magnetics, of the magnetic field. You have little pointy vectors showing which direction the local residual magnetic vector is pointing in when there's any field strength above the IGRF. When you have a field, potential field and you want to deal with gradients, it becomes imperative. It is imperative that you manage the sign of the gradients. I like to talk about the right-hand rule, and you can see the hand there, where, if you may remember from your first year physics class at university, the thumb is up with your holding your right hand. That means the Z is up. So in geophysics, or potential field geophysics, gravity, the convention is positive down by long-term convention. If you're measuring gravity gradients, one of the contractors, Bell Geospace, has the convention of east-north down for the X, Y and the Z. The Falcon system has northeast down. The magnetic field, as represented in the IGRF model, has northeast down. And there's a German magnetic tensor system called the IPHT, and that started life with east-north up. I believe that's changed to northeast down now. So the reason we're talking about this is that Intrepid has the capability of managing the sign of the gradients and allowing you to specify that, so that once you know what the convention is, you can put it in, and you can be sure the software actually takes care of applying the gradients in the correct signed manner. If you get it wrong, it can be horribly wrong. The created grid options also include enhancements to the TMI if gradient data is available, and the gradient data would show up as perhaps wingtip data, horizontal gradients. Perhaps if you have a formally measured field, a vector field or tensor field, there are many innovation options and enhancements such as phase, scalar magnitude. The list is up to 22 items long. An example, so the worked example of the demo will be held over to the end of this, this talk. I'll just give a highlight of what that's going to look like now. It's to do with the Amadeus Basin. It's a variable gravity gridding example. I show in the right hand side there the protobuf expression for a job, which is designed to do exactly what I was going to do in an interactive manner. And there's a usage message there. You run the tool with the batch language, and that's the file that I'm on the right hand side. That's the name of it there. So you just simply use it on the command tool, and off she goes. So on the left hand side we see the Northern Territory gravity point data, very variable. The Amadeus Basin is just down here in the bottom sector. So there's a reasonable density there compared to the rest of the Northern Territory. And then when we zoom in and subsection in on that area there, while we're actually gridding it, you'll see that we're talking about the Goss's Bluff version of the Goss's Bluff area in the Amadeus Basin, and this is a subsection of the data there. And the second stage of the gridding, as we multi-grid, we create an estimate of the long wavelength, and then we weed out or extract the high frequency portions of the grid for a second or third treatment to improve the high frequency content. So this is showing you the long wavelength where we know we're not going to revise our estimate of the grid there, and then the finalized version there. And this is a rather tough way of visualizing it with gradients and enhancement. We don't believe in Intrepid of hiding the warts. We think it's important you actually see everything. So if you look carefully at this little area I'm pointing out there, there's an impact structure that's called Goss's Bluff, and there it is. And looking at the satellite image, you can see the impact structure registered where the gravity is also shown it to be. So a word about regional gravity databases. Geological Survey land gravity stations in Australia were initially designed to be at every 11 kilometre, and so that remains the basis of the first estimate of the gravity field for Australia. And of course there's gravity sampling down to 200 metre spacing, and that's mixed in with it. So typically you would like a cell size of 100 to 200 metres to get the value from the closely spaced data. At 500 metre cell size, a one vertical derivative of the grid shows pimpling at its observation points. Varying the grid parameters doesn't help. That's why we invented this new method, to try and optimise the ability to get a best representation of the gravity field, when the reality is you have such a diverse sampling strategy that's gone behind creating the database. So the aim is to cope with areas of high and low data density, avoid compromise on the ultimate grid cell size, avoid artifacts that occur with single pass gridding in low density areas. So we use multiple passes starting with a coarse grid, and this has been used successfully not only on terrestrial gravity data, but it's been used where there's also areas of high aliasing in such as marine ship track gravity and mag data. So how do you improve your gridding practice? What constitutes a good potential field representation? Here's some war stories, I guess. We have some examples from some time ago that have been tabled maybe 6 or 10 years ago, where there's been discussions about this very subject. Grid A is a representation of the field, probably known, and here we have algorithm A, in this case showing up in the C term, and we're inviting you to have a look at the area there. You get this sort of discrete balling as the interpolation algorithm struggles to connect the dots. That's typical along linear features at 45 degrees to the sampling. Another one there on the B, you could see arguably a small artifact, some sort of distortion of the shape there in the B, and in the D another representation entirely of the field there. So for the very same input data you get lots of variability in outcome, and I would hazard a guess, if you're going to use just any gridding algorithm you happen to put your hands on, you would be subject to the same artifacts, and therefore could be badly misled in interpreting that data based on the grid. You might end up drilling a target and it could end up in tears because there's nothing there. As it turns out, the anomaly is driven by a gridding artifact, not by the data. So back to my other point about anomalies being centered above a line. So for standard scalar gridding, we've listed some anomalies 1, 2, 3 and 4. Now the maths and the physics of the standard gridding algorithms, if you don't have the benefit of gradients, you'll see, say on that top right hand one, you get what we might call a fried egg, and it's centered directly above the line. So you say, well, that's probably pretty good. But if the anomaly is not centered on the line and there's no special reason because there's no gradients, you would then worry about the gridding algorithm. Let's see what else we have here. Another representation of the same data. Yes, so if you look particularly at this bottom right hand side, the two bottom grids are every second line has been dropped out. So this is a deliberate attempt to expose the gridding algorithm to see how it behaves when the data is more aliased. And most unfortunately, particularly on the right-hand side at the bottom, there are anomalies that just can't be true because the anomalies are not centered upon lines. So this it's a brutal way of testing a gridding algorithm, but it's something that's well worth doing, and then having a good hard look at seeing whether the estimate of the field contains any anomalies centered between the lines rather than above the lines. So knowing that sort of problem, there are extensions to potential field gridding which have been invented by Intrepid in particular and others, and the aim is to get an enhanced total field estimate. So the extensions to traditional geophysics potential field gridding methods of a kima spline and minimum curvature. So here's an example of before and after, what we call the before and after gradient enhancement. It's the Baker data set. It's an Australian example, and in particular I invite you to look at some of the features that are more at a right angle. So if you pick up that feature there, you see the dots there without the gradients. As soon as you bring the gradients in, that feature straightens out and gets a nice edge to it, and you can see that's repeated quite often between the left and the right hand side. So the magnetic the total magnetic field is greatly enhanced when the features are inclined to the line direction, say 45 degrees, and you have gradients. You get a much better representation of the field if the job is done well. There's that example there, as I just said. Another way of being critical of a gridding job is to do a visual enhancement, which using the grayscale technique. So the eye is when it sees colour, tends to see lower frequency information, and grey or blacks, the grayscale is used when you want to see high frequency information. So this is an enhancement, this time of a Chevron magnetic data set from likewise 10 or so years ago, where you have the breakup of that dike-like feature, and then with the gradients it straightens out very nicely. And once again, you can compare the detail of some of the features that have been gridded and see how the coherence of local features is preserved once you have the benefit of also having local gradients to help inform the gridding process. In the Intrepid tool, which I'm talking about today, there are enhancements to gradient gridding. Included inside the algorithm are integrated heading corrections. There's an ability to specify a noise floor, and for magnetics you can specify not only the TMI but plus 2 horizontal gradients. That is supported feature of the tool. And similarly for gravity, if you have a measure of the gravity field, which is the GZ, we also support the possibility of having gravity components, if they're measured, of what would be in tensor terms a GXZ and a GYZ, which is simply the horizontal gravity components. And some airborne gravity instruments are measuring these, e.g. the Sanders airborne system. Gradient gridding extensions. So the next step up from the two vector components, horizontal components, goes to the full tensor gridding. What benefits accrue if you have a whole tensor that's been measured? The line spacing at which the resolution can be successfully maintained is 50% reduction up to 50% reduction in the cell size when a full tensor gravity or magnetic gridding is attempted. All the measured gradients, if they're transferred from the line data into the grid, then become available for geological interpretation, such as if you wish to estimate strike or depth or tilt, thicknesses and density contrasts across a fault. By having more of the measured signal carry through to the gridded stage, a lot of extra, you've paid for the survey, you should insist that the signal that you've paid for makes its way right through to the point where there's an interpretation capability of using all of the measured gradients. So the benefits of full tensor gridding: what was measured remains available for longer. You can use all the tensor so better resolution is possible. You can widen your line spacing and still achieve survey goals. We provide a QC technique to show how well data is being delivered by contractors. Visualization of the gradients and other properties for interpretation become important. And there are a range of tensor fast Fourier transform filtering for the whole signal. It becomes a lot easier when you have the data represented in a grid form. Having created the grid representation of the tensor gradients, it's not subject to this particular talk, but the integration of the field from the gridded form of all the tensors becomes a lot easier to estimate either the vector version of the field or in fact the scalar version, just by using fast Fourier transform methods. Here's a graphic that Belgium Space produced a couple of years ago, which was designed to demonstrate the ability of decreasing the cell size when you have the full tensor measurement. And more or less, it's the traditional gridding would give you a cell size of 1, or 4 between the lines, and this would go to 6 or 7 as soon as you have the full tensor available. In recent times, Intrepid has also invented a special gridding algorithm for Falcon data. The Falcon tensor measurement is different to the full tensor. We have a horizontal gradient measures in the Falcon system. We have a horizontal gradient measures in the Falcon system, but the disk is such that it allows you to have repeat readings, A and B. These readings are meant to be in the horizontal plane. In our invention, we treat these readings as being analogous to a complex number, and we can interpolate 2 or 3 readings to estimate the Falcon view of the gravity tensor on a regular grid. We do that using the same slurp algorithm, but in this case we're only using it in the one plane. And so let me just explain that for you. If you have an observation at P0, this is like a pseudo-Moore circle. You have the TUV in the horizontal plane, the TXY in the vertical axis direction, and by plotting the observed TUV and TXY at one point, and then the second observation at some spatially removed point nearby, you have a different TUV and a TXY, and you wish to estimate on a smoothed curvature basis between those 2 observations around the arc. That's basically the slurp process. And so we wish to estimate P, which is some point spatially separated, and we turn that spatial separation into an angular separation, and we use the sine method down the bottom here, where T is the distance operator between P0 and P1, and the angle is the omega between P0 and P1, and we estimate the value. We estimate the Falcon signal as a composite x, y, and uv by using complex arithmetic and this formula. Another gradient gridding extension for an enhanced total field estimate. Intrepid has been in this business a long while and has trialled many things. So quite a long time ago it was realised that a Fourier domain method, there are various options in Fourier domain that can exploit the relationship between potential field gradients to produce a grid. So we have another tool. It's not in the main gridding tool, which we would make available to you if you purchase the gridding tool, so you can try it yourself. And it's based on using Fourier domain methods to create an estimate of the TMI, or the vertical derivative. And the theory goes like this: the horizontal gradient gridding using the Fourier domain, we have measured gradients, and say a total field are related by the following Fourier domain equations. If you take the Fourier transform of the vertical component of the field, and you know the wave number, that's a simple Fourier domain of the transform of the total field by the wave number would give you the vertical component. And similarly, that same vertical component in the Fourier domain is an addition of the two horizontal components in the Fourier domain multiplied by the wave number in the x and y direction, and then a scaling factor -1 over the total wave number. And the final one down the bottom you can estimate. So that's basically, if you have the two horizontal gradients, you can estimate the vertical gradient, or if you have the two horizontal gradients, you can estimate the total field by a simple Fourier domain arithmetic. So we have the tool here. We're not going to demonstrate it, but I'm just going to illustrate it. And it simply pops up. It's like a wizard. Asks you for the horizontal gradient in the x direction, horizontal gradient in the y direction, and what do you want to do. You've got a filtered grid, and you just push the button and out you get. So we're showing here the illustration of an east-west component grid, a north-south component grid. We put them through that tool and you get a combined Fourier method. So I must say it's worth revisiting this technology from time to time, because in working with gradients in recent times, we've learned a few more tricks about padding, and they could be usefully applied back in this technique. This was first trialled maybe 10 years ago. Now we get to the end of the talk, and we'd like to give a practical demonstration, and that's an introduction to the gridding of potential field data, and I hope that you found that informative. Good afternoon. My name is Des FitzGerald. The live demo from the south of the Northern Territory in Australia of the Amadeus Basin, where we have some variable gravity data, and I'm going to show you how to get an optimum gridded representation of the field. So let's begin. So now we start on a demonstration, and the practical demonstration is to do with taking the Amadeus, we're going to highlight the Amadeus Basin data. We're going to extract it from a Northern Territory gravity principal facts database. So the Northern Territory principal facts database, you can see it there labelled ntgrav.dir, and we're just exercising the project manager. Looking at the thumbnail, you can make out the Northern Territory, and we're now going to fire off the 3D Explore tool to continue just exploring what the data looks like. and that comes up by default with the fields across the top, the row, the group, the bouquet, the free air, the original observed gravity field, and just simply a Latin along. And so at this stage the data is in lat long projections, and yeah, so they're just expanding the view, and you can see across the top the longitude. We're zooming in and seeing the very variable nature of the sampling of the gravity field in the Northern Territory, and that's the purpose of this demonstration, to try and optimize the frequency content despite the variable data sampling. The mouse is coming down from the towards the bottom of the Northern Territory, where the Amadeus Basin is, down here, and that's the area we're going to subsection out and zoom in on. So that's the end of the quick preview of the data. There are the fields, and you can see they're all 3-byte real except for the Latin longs, which have to be, you need the double precision to get the sufficient resolution. Now we fire up the gridding tool, and you see the same image we saw before as the preview. Instead of using observed gravity, we're going to do the bouquet corrected. So that'll be slab corrected bouquet, it's not terrain corrected, just the simple bouquet correction. And the first thing we're going to do is choose to increase the extrapolation in cells, but from 5 to 10, and when a cell, when an observation arrives at the minimum in a cell, we're going to take the point that's been observed that's closest to the centroid of the cell as the observation that we're going to honour. That's what we call an original data point. The variable gridding methods, we're going to use the variable density method. It's variable data density, which is perfect for this type of thing, and it's a multi-grid method, so you have reduction factors from one grid to the next. So we're picking out say from 5 to 1, and then for the coarser grids, the original grid that we're going to start with to get the long wavelength, the historic data, we'll we'll do 20 iterations of minimum curvature on that, and at the longer wavelengths, and we won't weight any sample any differently to any other, so just use unity weight types. So the first grid will be have 5 times the cell size as the final grid. Now moving on to the grid refinement stage, you do a small amount of initial smoothing. That's what the Laplace operator is. You don't need to do very much of that, and that the reason for having that there is just to make it go a bit faster when it comes to enforce the the minimum curvature. And there are 3 kernel sizes in minimum curvature. I actually like the 49 one, but today we're going to use the 25. We're not going to have a maximum residual we're prepared to leave in the data. We'll just let it run for the 70 iterations. And traditional relaxation factor is an over-relaxation for the Gauss-Seidel solver for the minimum curvature, and it's always it's been shown by historic practice that 1.375 is a good one. Now you can honour the original cell data to the nearest cell or the nearest 2 cells, as I've shown in the previous thing, and then when it's finished doing the minimum curvature, we can relax the honouring to enforce the minimum curvature kernel just a little at the end to take off any hotspots. We want to fill any internal holes, and we're going to extrapolate to the limits of the data. We now move to the output panel. We're setting up the name of the grid that we wish to produce, and we're just calling it Bouquet M.
The product name is Bugay, so it just inherits the field name as the default. The null value will be -999 by default. The precision will be inherit from the input field, so it'll be 4-byte real. And we're setting now the ultimate cell size, which is quite a fine cell size. It's down to 0.002 of a degree, which is approximately 220 meters. You can see that on the side there. So it's quite a big cell size by default. If it was the whole of the Northern Territory, 5,000 by 8,000 cell size. But now we're going to limit the region by just typing in, an origin point, which is right down there. You can see it's moved right down, and then we're going to take the extents in degrees and limit it to, we limit ourselves to a grid which is 1400 columns and 1200 rows at 220 meters, and we've set our origin points on the top left hand corner. Then you get the, we've hit the apply button, and automatically, so the first thing we do is create the the course grid, and then as the first pass, and we smooth that pretty strongly to get the long wavelength where the data sampling is inadequate to support the high frequency 220 meter grid that we want. And when there's plenty of observations of the gravity as point data, we get the we cut it out and allow the grid, the second pass, to honour the higher frequency. So there it is already. It's quite quick, and we have our first version of the data, and there's the grid, and in the thumbnail immediately shows up in the project manager in the thumbnail, and we can go straight to 3D Explorer and try and enhance the grid, and just do a bit of data enhancements. We're going to do the color stretching. So you open up the right hand bar, the toolbar there, and we've turned on use the signal for the Z-axis, and we're going to rotate that in 3D. So you get a visual effect using the gridded Bugay as a relief. So it's only 100 or so milligauss, but it's scaled. That is, can be a useful way to show you the variation of the gravity field. So there's a job file here, of course, that also does exactly the same job. So what you did interactively is also available, and there are all the options that we chose, and you can see them there. You can see the cell size, the field name, the number of iterations, the fact that we're using the lat and the long, and the field from the database. And we can run the same job interactively, but as using a task file rather than running the GUI. And there it is running, and instead of the grid being called the Northern Territory Grav Bugay, it's now called the West Amadeus Bugay grid. It's exactly the same size, and you can see the progress bar happening in the top right hand corner, and the job is finished. You get a pop-up to say that the interactive job is finished. And now we'll have a look at that one as well. It should be identical to the one we did interactively, and we're looking at the histogram of the Bugay, and you can see it's ranging from up to 300 milligauss, and you get the same histogram with the second grid. Yep, fine. And they're just switching between the two thumbnails. You see it's the same product. So one was done interactively, one was done. And we're using the older visualization tool now, and one of the reasons for picking that up is it also does automatically the wet look, and also the gradient drape. There's the range of the data being shown there, histogram equalizing it, and this is a much tougher, well, once we go to the drape, it's a much tougher way of looking at the data to see what the busts were. So this has been recorded, and that ends the demo. Thank you very much.